In the last few lectures, we were looking at high Peclet number flows past a surface with a no slip condition at the surface. Okay. We are looking at forced convection and consider the limit Peclet number much larger than 1. Okay. We did, for example, the flow past a flat surface of length L with the x coordinate in the streamwise direction, z coordinate in the cross stream direction, and we found that there is a boundary layer thickness, okay, within which convection and diffusion are comparable even in the limit as convection as the Peclet number becomes large, and this boundary layer thickness goes as x power 1/3 okay, for the flow past a flat surface, and we got the Nusselt number proportional to Peclet number power 1/3. Okay. And recall that we had defined the scaled variable eta is equal to z by delta of x, okay, and use that to get a similarity transform. Okay. And that similarity transform would give us an equation of the form something, okay, some term into minus eta square dt by d eta is equal to d square t by d eta square. Okay. We also solved a stagnation point flow, okay, where we had a flow looking like this: x z Vx is equal to k x z, Vz is equal to minus k z square by 2. And we got this exact same form times an additional term which was different. Okay. So, the blue was different in the case of a stagnation point flow, the red part was exactly the same, okay, and similarly for the flow past a sphere, okay, where you had flow going around the sphere, okay, of radius r. There again the Nusselt number was proportional to p power 1/3, suitably defined. There we had defined the similarity variable as the scale distance from the surface divided by the boundary layer thickness. In that case also the red part was exactly the same, the blue part was different. So, why is it that in all these cases the expression for the temperature field in terms of the similarity variable turns out to be exactly the same, okay, and the boundary conditions for the temperature field are also exactly the same. What only changes is the expression for the variation of the boundary layer thickness with the streamwise coordinate. Okay. The only thing that changes is the expression for the variation of the boundary layer thickness with the streamwise coordinate. Okay. So, why is it that we get the exact same expression? Okay. So, that we can understand by looking at the case of a general flow field. Okay. So, let us say that you had some variation in this, okay. The variation is typically, assumption is that the radius of curvature for the variation in the height is small is large compared to the boundary layer thickness. Okay. So, in the case of this for example, the boundary layer thickness is small compared to the radius. Okay. The boundary layer thickness is small compared to the radius, okay, except at the downstream side where you have the downstream stagnation point. Everywhere else the radius of the sphere is small compared to the boundary layer thickness, the radius of the sphere is large compared to the boundary layer thickness. So, that within the boundary layer it is effectively like the flow past a flat plate. Okay. So, in this case as well I will assume that the boundary layer thickness is small compared to the radius of the radius of curvature of the variation. Okay. And locally I can impose a coordinate system x and z. X is the streamwise direction, z is the cross stream direction. Okay. In general these variations could be 3 dimensional as they were in the case of the flow past a sphere. I will restrict attention to 2 dimensional variations. Okay. If you have a no slip condition at the surface, okay, then you would expect that the velocity will increase linearly from the surface. the streamwise velocity will increase linearly from the surface. Therefore, the velocity Vx is going to be equal to some velocity gradient Vs prime times z. Okay. It is going to be equal to some velocity gradient Vs prime times z. Okay. For an incompressible flow, we also have the mass conservation condition. Okay. Partial Vx by partial x plus partial Vz by partial z is equal to 0. Okay. Note that this Vs prime can in general be a function of x. Okay. Vs prime is in general a function of x. Okay. This has to satisfy the mass conservation equation. That means that partial Vz by partial z is equal to minus z dVs prime by dx. Okay. Which means that Vz is equal to minus z square by 2 dVs prime by dx plus a constant. That constant has to be 0. Okay, that constant has to be 0 because at z is equal to 0 there is no penetration into the surface. Okay, at z is equal to 0 there is no penetration into the surface, therefore, that Vs prime is equal to 0. Therefore, I have the velocity components Vx is equal to Vs prime of x times z. Okay. Vz is equal to minus z square by 2 dVs prime by dx. Okay. Energy equation. Okay. Vx partial t by partial x plus Vz partial t. Okay. I will just write in terms of the scale temperatures. Okay. For now, I will just write in terms of the scale temperatures. Is equal to alpha times partial square t by partial z square. Okay. And I substitute for x, Vx and Vz close to the surface. Vs prime z, and this has a minus z square by 2 dVs prime by dx. Okay. For the flow past a flat plate, Vs prime is a constant. The strain rate is independent of downstream coordinate. Okay. If you recall, for the stagnation point flow, we got Vx is equal to k x times z. Therefore, Vs prime is equal to k times x. Okay. Vx is equal to Vs prime times z, which is kxz. Therefore, Vs prime is k into x. Okay. So in general, this Vs prime is a function of x. And then we do our substitution. Okay. Eta is equal to z by delta. Okay. Partial t star by partial z is equal to 1 by delta dt star by d eta. Partial square t star by partial z square is equal to eta square. Okay. And partial t star by partial x, okay, is equal to dt star by d eta into, if you recall, we got it as minus eta by delta d delta by dx. Okay. Minus y by delta square, minus z by delta square d delta by dx. Okay. Because derivative of z by delta is minus z by delta square d delta by dx. Z by delta square is the same as eta by delta. Okay. So, you can substitute that into the governing equation. Okay. We can substitute that into the governing equation. Okay. Vs prime delta eta, okay, to partial t by partial x. Okay. So, this is minus eta by delta d delta by dx dt star by d eta, okay, minus minus z square by 2. Z is delta eta. So, z square is delta eta the whole square by 2, okay, dvs prime by dx, okay, into partial t by partial z, that is 1 over delta dt by d eta. Okay. This is equal to 1 over delta square d square t by d eta square. Multiply throughout by delta square and collect terms. Okay. You can easily see that there is an eta square multiplying each of the two terms. Okay. Each of the two terms, okay, there is an eta square multiplying each of the two terms, and there is a negative sign. I can collect those together to get minus eta square dt by d eta. Okay. This whole thing into a factor in front. Okay. And what is that factor? Okay. This will be Vs prime delta square d delta by d eta plus delta cubed divided by 2 dvs prime by d eta. Okay. And I made a mistake here because I have to have a thermal diffusivity in front. Okay. So, I should put the thermal diffusivity there, okay, 1 by alpha, okay, is equal to d square t star by d eta square. Okay. And you can easily see that this term is the same as what we had for the sphere, flow around a sphere, flow past a flat plate, stagnation point flow, and any other flow which satisfies 0 velocity boundary condition at the surface and which satisfies this incompressibility condition, okay, and which satisfies this incompressibility condition. Okay. Any flow that satisfies the incompressibility condition and the 0 velocity condition at the surface ultimately will give you minus eta square dt by d eta is d square t by d eta square. Okay. So, that is what you will ultimately get. This term, okay, depends upon the functional form for Vs prime as a function of x, okay, and you require that 1 by alpha into Vs prime delta square d delta by d eta plus delta cubed by 2 d Vs prime by d, sorry, these are derivatives with respect to x, not with eta. Okay, dvs prime by dx, this is equal to 1. Okay, this has to be a constant for a similarity transform. That constant can be set equal to 1 without loss of generality. Okay, that constant can be set equal to 1 without loss of generality. Okay. Delta square d delta by d eta can be written as d of delta cubed. So, this can be written as 1 by 3 d delta cubed by d eta. Okay. 1 by 3 d delta cubed by d eta. Okay. Once again, my apologies, this should be x because delta is a function of the streamwise coordinate x. Okay. I can multiply throughout by alpha. Okay. So, I will get an alpha on the right side. I will get an alpha on the right hand side. Okay. And divide throughout by this prefactor, divide throughout by this prefactor to get a first order differential equation. Okay. Divide throughout by this prefactor to get a first order differential equation. Okay. So, this will give me d delta cubed by dx plus 3 delta cubed by 2 V s prime d V s prime by dx is equal to 3 alpha by V s prime. Once again, making a reference to the first order differential equation dy by dx plus p of x y is equal to q of x, we find that p of x is equal to 3 by 2 V s prime d V s prime by dx, okay, and q of x is equal to 3 alpha by V s prime. Okay. Therefore, the integrating factor, okay, is equal to e power integral p dx. Okay. Dx into 3 d V s prime by dx. Okay. Okay. Of 3 by 2 into d log V s prime by dx. 1 by v dv by dx is d of log of v by dx, okay, and 3 by 2 times log v is just log of v to the 3/2 power. Okay. So, this is equal to e power integral dx into d log v s prime to the 3/2 power by dx. Okay. So, this is just exponential of log of V s prime to the 3/2, okay, which is the same as V s prime to the 3/2. Okay. Therefore, the expression for delta cubed, okay, is equal to a constant by V s prime to the 3/2 plus, okay, 1 by V s prime to the 3/2 integral 0 to x dx prime, okay, of 3 alpha by V s prime into V s prime to the 3/2. So, this is c by V s prime to the 3/2 plus 1 by V s prime to the 3/2 integral 0 to x dx prime. Okay. I can take the 3 alpha outside, into V s prime whole to the half. Okay. So, that is the expression for the boundary layer thickness for a general 2-dimensional flow. Okay. The requirement that the boundary layer thickness, okay, delta is equal to 0 at x is equal to 0. X is the start of the heating section. At the start of this heating section, the boundary layer thickness has to be 0. Therefore, the requirement that delta is equal to 0 at the start of the heating section, that is x is equal to 0, implies that c is equal to 0. Okay. And therefore, the boundary layer thickness is delta cubed is equal to 3 alpha by V s prime whole power 3 by 2 integral 0 to x dx prime into V s prime whole power half. So, that is the expression for the boundary layer thickness as a function of V s prime, which is a function of x. Okay. So, for this general flow field, I have shown you, provided the flow is incompressible, that is, this incompressibility condition is satisfied, okay, and the boundary layer thickness is much smaller than the characteristic length scale of the flow or the characteristic length scale of variation of the surface. Okay. If the boundary layer thickness is much smaller than the characteristic length scale for the surface variation, we can effectively consider this surface to be a flat surface as in the diffusion part of the equation. Okay. In the diffusion part of the equation, for the del alpha times del square t, you can consider the surface to be a flat surface. Substitute these expressions, these general expressions, for the velocities in the streamwise and cross stream direction close to the surface. With those general expressions, we find that there is a universal form for the temperature field as a function of the similarity variable eta. That has a universal form, provided there is a no slip condition at the surface, regardless of what the nature of the surface is. Okay. What varies, what is a function of the velocity profile, is the variation of the boundary layer thickness with the streamwise direction, and we have obtained an analytical expression for, or rather an integral expression, if you have a specific form of V s prime, right. If you have a specific form of V s prime, you can calculate what is the boundary layer thickness, okay, just from the variation of the strain rate at the wall with the streamwise direction, okay, just from the variation of the strain rate at the wall with the streamwise direction. You can verify consistency, okay, for a flat plate. Okay. V s prime is a constant. It is independent of downstream distance. Okay. It is independent of downstream distance. V s prime is a constant. Okay. Therefore, delta cubed is equal to 3 alpha by V s prime whole power 3 by 2, okay, into V s prime to the half times x, because V s prime is a constant. So, you just get V s prime to the half times x, okay, is equal to 3 alpha x by V s prime. Okay. Which implies that delta is equal to 3 alpha x by V s prime whole power 1/3. This is exactly the same expression that we had got for the flow past a flat plate. Okay. Stagnation point flow. Okay. Vx is equal to kxz, okay, which implies that V s prime is equal to k times x, okay, because the velocity Vx was equal to V s prime times z, okay, close to the surface. Therefore, delta cubed is equal to 3 alpha by kx whole power 3 by 2 integral 0 to x dx prime, okay, k to the half x to the half, okay, k to the half times x to the half, okay, is equal to 3 alpha by kx whole power 3 by 2, okay, into k to the half, okay, into 2 by 3 x power 3 by 2. That is what you get when you integrate x power half. Okay. It is x power 3 by 2 divided by 3 by 2. Okay. Okay. And this is equal to 3 alpha okay. You can see that the x to the 3 halves will cancel out in, okay. So, 3 alpha into 2 by 3 into 2 by 3 k, okay, which is 2 alpha by k. Okay. You can see the x to the 3 halves will cancel out in the numerator and the denominator. Okay. which implies that the boundary layer thickness delta is equal to 2 alpha by k whole power 1/3 for a stagnation point flow. Okay. Stagnation point flow, you recall, was the flow towards the surface. Okay. There we had found out that the boundary layer thickness is a constant, it is independent of x, and that value is given by 2 alpha by k. That is precisely what we get from this calculation as well, whereas this one was for a stagnation point for the flow past a flat plate. Okay. Okay, this one was for the flow past a flat plate, okay, where we had a boundary layer increasing with x. Okay. So, this can be done for any form of the velocity, any form of the function Vs of x. Okay. For any given form of the variation of the velocity, the strain rate at the surface with the downstream distance for 2-dimensional flows. Okay. This is the expression for the boundary layer thickness. Once we know what is the boundary layer thickness, then we know that Qz is equal to minus k into Tw or T naught minus T infinity by delta, okay, into dt star by d eta at eta equals 0. Okay. dt star by d eta at eta equals 0 is just given by 3 power 2/3, it is just a constant, 3 power 2 by 3 by gamma of 1 by 3. Okay. Average, okay, this should be a negative sign here, the slope is negative at the surface, dt by d eta is negative at the surface. Okay. Q average is equal to k into T naught minus T infinity, okay, into 3 power 2 by 3 by gamma of 1/3, okay, 1 by the characteristic length integral 0 to L dx 1 by delta. Okay. And the Peclet number is equal to Q average, okay, divided by k into T naught minus T infinity by L. This will be equal to 3 power 2 by 3 by gamma of 1/3 integral 0 to L dx 1 by delta. Okay. Sorry, this is the Nusselt number, not the Peclet number. Okay. The Nusselt number or the Sherwood number. Okay. And delta we know as a function of Vs prime. Okay. Delta we know as a function of Vs prime. Okay. So, you can write this as okay. Substitute this expression for delta for a known value of Vs prime in order to find out what is the Nusselt number. Okay. So, that was the reason why the temperature field in terms of eta was the same. The T star in terms of eta was the same for any configuration where you have a no slip boundary condition at the surface, provided the flow is incompressible for 2-dimensional flows. What happens if we do not have a no slip condition at the surface? We saw one of those problems earlier. Okay. We saw one of those problems earlier, which was a falling film. Okay. And recall that the velocity profile was a parabolic profile. Velocity was non-zero at the surface, okay, and you have gas that was diffusing in, okay, gas that was diffusing into the surface, okay, gas that was diffusing into the surface, and you had a boundary layer thickness close to the surface where the surface was mobile, it was moving with a constant velocity. In that case, what happens? Okay. I will discuss that in the next lecture. We already calculated the correlation for this particular configuration of a falling film. I will discuss in the next lecture a slightly different configuration, which is the diffusion around a gas bubble in a liquid, okay, where there is a non-zero velocity at the surface of the gas bubble. I will continue this in the next lecture. Okay. I will see you then.